Hello guys, welcome back to my YouTube channel. And in this video, I'm going to describe the three basic sorting techniques. In the upcoming video, I will also upload the videos for quick sort and bubble sort. Sorry, the quick sort, heap sort, and the merge sort as well. But in this today's video, I'm going to explain selection sort, insertion sort, and bubble sort. So let's get started. First of all, let us understand what bubble sort is. What we do in bubble shot, that we just like when bubbles, for example, there's a bucket and there is water in it. Okay. And if there's water in it in a bucket, then what we do, all the bubbles that are bigger in size comes to the front of it. Okay. So this is the basic idea of bubble shot. In bubble shot, we repeatedly swap the adjacent elements which are in wrong order. And due to this repetitive sorting, the element which is the largest comes to the end of the array. The largest element comes to the end of the array. So in bubble sort, we compare adjacent elements and swap. If the left element is bigger than the right element, then we swap those elements. And we repeat till no swaps happens. Okay. So this is the basic idea of bubble sort, but how bubble sort actually work. And this is the code. So let's see the code. But let me just first explain to you how bubble sort will work. So, like for example, this is the array. Let me just adjust it for some, like this is the array. Okay. And in this array, let us just say that this is the unsorted array. And in this array, if we try rep- to arrange the adjacent elements, we will check first 10. Is 10 greater than 2? Yes, it is. So I will swap 10 with 2. Okay. Then I will check 5 and 10. And since 10 is greater than 5, I will swap 5 and 10. Okay. Then I'll check 3 and 10. Again, the same thing. I'm going to swap it. Okay. Now 6 and 10. Again, the same thing. I'm going to swap. And again, the same thing. We see by swapping adjacent elements when the right element is lesser than the left element we have swapped, and sorry, the 10th, the element with the value 10 comes to the end of the array. So up to this portion is sorted now. So we have to repeat this process of swapping until all the elements are sorted. Now we will check for 2, then we will, since 2 is not greater than 5, we will move to this element 5 and 3. Since 5 is greater than, so we will swap these two, 3 and 5. If we'll again check 5 and 6, since there is no comparison, we need to swap them, 4 and 6. So with this swapping, 6 is placed at its right position. So this adjacent swapping is used to do the bubble sorting. The bubbles which are larger by adjacent swapping comes to the end of the array. And this is the code for this. We will do this swapping for n minus 1 times, 0 to n minus 1. Why would we do for n minus 1 times? That's because the first, because we don't want the last element will be already sorted. We are doing for this, for this, for this, for this, for this, and the last element will already be sorted after all the swappings. So we are doing it for n minus 1 time. The outer loop will be for n minus 1 times. And since if the array is already sorted, then no swaps will occur in the first iteration. The first iteration will be done and no swaps will occur. That's why we are maintaining a variable swapped. And we are assigning it the value false for the first time. Then for j equals to 0 to j is equals to n minus I minus 1. Why are we doing n minus I minus 1? Because after the first iteration, the 10th value would be sorted. So we don't want to go up to 10th. Okay. After the second iteration, the n minus 2th value will be sorted. We don't want to go up to the sixth value to check. Then after the third iteration, don't want to go to up to this fourth value. So we are doing n minus I minus 1. Okay, for the inner loop, we are doing j equals to 0 to j equals to n minus I minus 1. Now we are, for every iteration, we are checking if the jth index, this is the jth index, if it's greater than the j plus 1th index. So for the first iteration, j equals to 0 and j plus 1 is equals to 1. We'll check both of them. If this is greater than, then you'll use the simple swap code and make the swapped variable true. The swapped variable, we will assign it the value true. So if, and we will check after this for loop, we will check if the swapped variable is still false. If it's still false, then we'll break because the array is already shorted. That's why the best time complexity of this shorting is big O of n. Because if the array is already shorted, we will break out in the after the first loop only. So order of n is the best time complexity. Average time complexity, since there are two loops, is order of n square, and the worst time complexity is as well order of n square. Space complexity is order of 1, and because we are not using any extra space in it, and it's a stable algorithm. What do I mean by stable algorithm? The relative order of the elements which are same does not change. What do I mean by this? If there were two fives in it, if in this array there were two five, one five, let's suppose there were two five. Let's suppose this was the array. And if I were to swap the array, if I were to swap the element, then this swapping will never occur. There will be no swapping in 5 and 5 because we are checking if the left element is greater than the right element. This swapping will never occur. So the relative order of elements which are same, the relative order, if elements have the same value, they maintain their relative order. So these types of algorithms are called stable algorithms. So this algorithm is stable. Okay, I think we all understood the dry run for this. So let's go to selection sort. Selection sort. What is the selection sort? The idea behind selection sort is we take we we want to take the first element and we suppose that this is the shorted part. And we what we do is we find the minimum element from the unsorted part and place it at the beginning. So the idea behind selection sort is finding the minimum element from that from the part of the array and then coming back and placing that element at the first of the array. And up to this, the array will be shorted. So, for example, let's suppose this is the dry run for this. So I have 5, 3, 1, 4, 2. This is my merge sort example for the merge sort array. Okay. So this is it. Now, what I do is in iteration 1, I will find from 0 what is the minimum element which starts from 0. We find 1 is the minimum element. So I will swap 5 with 1 and 1, 3, 4, 1, 3, 5, 4, 2 would be the array. For the second iteration, what would I do is I would find minimum element from the one index, 0, 1, 2, 3, 4. There are four indexes from the second index, from the one index. I will find the minimum element. The minimum element from this index to this, after array be shorted to this, from this index to this is 2. So I will replace 3 and 2. So 2 will come here and 3 will come here. Okay, I will again find minimum element from this index from 5. From 5, the minimum element is 3. So 3 will come after 2, and 4 and 5 will be there. And I will find the minimum element from 4 from this index. From third index, the minimum element will be 4 only. So there will be no swapping. The array is sorted in this order. This is a very simple approach, I would say. Selection sort is even easier than bubble sort. Uh, this is the working approach. We assume the first element is minimum, compare it with the remaining elements, swap with the actual minimum, swap with the actual minimum. If the minimum is updated, then we swap it. And if not, we will still swap it, but with the same, if we swap with the same element, then the element will remain same. And we move the boundary of the shorted part forward. For example, this is the code, Java code for selection sort. We assume that n is the length of the array. We move from 0 to n minus 1 again. Why we move from n minus 1? Because the last element will already be shorted. Okay, the same thing we did in the bubble sort. The last element will be shorted after all the four. After we have shorted the four elements, the last element will already be shorted. That's why. And we move. we for I equals to 0 to n minus 1, we assume that the minimum index is 0. For the first condition, we in this we assume that the minimum index is 0, the five element. Then we move from I plus 1 to up to n, and then check if there is another minimum element. And if there is a minimum element, we update the minimum index. So for example, in this 3, 4, 3, 1, 4, 2, the minimum index will be updated with 0, 1, 2. 2 will be the minimum index. And then we swap the minimum index element and the element at the front, the one we are checking. And the loop will again go and again go. Since there is no check for early breaking, there is no check the array is sorted, all the time complexities for this algorithm will be order of n square. Okay. The space complexity will be order of 1 because this is an in-place swapping. Oh, but the major disadvantage is that this is not a stable algorithm. Okay. Why is this not a stable algorithm? Because we are swapping the elements which are also same. The elements which are same will also be swapped. That's why this is not a stable algorithm. Let's go to insertion sort, the last algorithm which I'm going to discuss today. In insertion sort, what happens is we sort the array one element at a time by inserting each element at the correct position. So what we do is we find one element and we try to put that in the correct position of the array. So we did swaps until we find the correct position for that element. Instead, in selection sort, what we are doing is we are finding the minimum element from one part and then put that minimum element to the forward. But in insertion sort, what we are doing is we take one element and we swap or we keep moving that element until we find the suitable position for it. So this is the driving for uh, insertion sort. We try to take, for example, I took 5, 3, 1, 4 to the same example again. What I do now is that I would think that this is the shorted part. This 5 is shorted. Now I will try to place 3 at its correct position. Would 3 come above, matlab, forward to 5 or backward? It will come forward to 5. So I will place 3 before 5. So 3, 5. Now I will think that this is a shorted part. And I will try to put 1 at its correct position. I will swap 1 with 5, then 1 with 3, and 1 will come to its correct position here. So it will have its correct position. And the same thing for 4 now. 4 will come replace with them, but not will not come before 3. So 4 will be placed at this position. So this pass is shorted now. And same for this. So this is how the insertion sort works. Let us check the working and the coding for insertion sort. Insertion sort, we take one element, we compare it backward, shifts the element right, and insert them the correct position. So we will start from 1 here, not from 0, because we think that the first part is already shorted. And we will try putting elements from this part to its correct position. So from 1 to a length of the array, we will take the index which we are at right now as the key and j as -1. Okay. Until the j becomes 0, j is greater than 0, j becomes less than 0, we will run a while loop. And the key, until the key is greater than, sorry, the air of j is greater than key. If this is greater than, we are checking for 1. For example, we are checking for 1. And 1 is greater than 5. Is 1 greater than 5? No. 5 is greater than 1. So the while loop will continue. We will come here. Is again 3 greater than 1? Yes. So while loop will continue. We will come to -1. So this condition will break. So okay. So at j plus 1. Since we came to -1, j plus 1 will be 0 and j plus 1 we will place the key. This is how we work out the code for this. The best time complexity is order of n for this because if there were no, if every element was its correct position, the while loop will never run. So, okay, the best time complexity is order of n, and the average inverse star order of n square, space complexity is order of 1, and this is also a stable algorithm. Okay, thank you. That's it for all. So, that is it for today, and in the next part, I will also upload the algorithms which are heap short, quick short, and merge short. Thank you.